Welcome back to the EasySpin Academy 2020. This is session number 6 of the first day. We're going to look a little more into detail into several other features of solid-state EPR simulations. So this is the last topical session. The next session will be a general questions and answers, where we'll pull some of the questions on Slido. And if you have questions you would like to answer us in the Q&A session, please post the questions on Slido or upvote questions that you're interested in, and we'll look through Slido in the Q&A sessions. All right, so for this session, we'll concentrate again on solid-state EPR. In the previous session, we've seen some of the basics, and now let's explore a few more features. First of all, high-spin systems. Let's take a triplet system, so sys.s equals 1. We're going to add some zero field splitting, D, say 1000 megahertz for the D value and 130 megahertz for the E value, and add some line width broadening, say 2. Then we'll simulate the X-band spectrum. Let's take 10 gigahertz for now, and just specify the sweep range, 300 to 420 millitesla, for example. And Pepper can easily simulate this high field, these high spin systems without any additional input except spin 1. There you go. Here you see a rhombic triplet spectrum of a thermally polarized triplet. But as you know, as many of you know, for a high spin system, you might also expect a double quantum transition, a half field signal. Let's see if that's there. So all we need to do for this is we need to change the range to extend down to the field value where we see the half field transitions. So let's go down to about 100, maybe 150 should be sufficient. So if you run the simulation, and voila, you have it. Around G equals 2, you see the single quantum transitions. These have delta ms equals 1. And down at roughly half field, you see a much weaker transition. That is due to the delta ms equals 2 transitions. And these are nominally forbidden double quantum transitions, but since there is Zeeman state mixing going on, they have appreciable intensity. So for high-spin systems, since Pepper EasySpin use exact matrix diagonalization, you will see all these semi-forbidden or semi-allowed transitions, and they can get quite complicated if the electron spin quantum number is very large. So a triplet is just the simplest possible high-spin system to demonstrate. Another important thing is temperature. Again, let's take the spin system from before. Again, our triplet with a rhombic detensor. Well, let's make the line a touch narrower. Let's take the same frequency, maybe just focus on the single quantum transitions between 300 and 420. And now let's add a temperature, exp.temperature. Let's run it at 2 Kelvin. So at really low temperature, and let's see what happens to the spectrum. So right now, I haven't run it yet. You can see the current spectrum. It looks nice and fairly symmetric. If you run this at 2 Kelvin now, I'm going back to this section here and pressing Control Enter or Command Enter. You will see that there's some slight intensity differences. For example, this line is more intense than this line. If you go even lower in temperature, it's an expensive experiment, but with EasySpin you can do it. You can see that the thermal polarization of this triplet becomes stronger and stronger. If you change the sign of the D value, you put a negative in front here, then the D tensor is negative. That swaps the energy levels around and will also swap around which levels are going to be populated in this low temperature range. Pressing Control Enter shows that now the spectral shape is inverted. So this is now the weaker transition than this. So EasySpin takes care of all the Boltzmann populations and calculates them accordingly. And we can, of course, always show the absorption spectrum by setting x.harmonic to 0. Voila, here's the absorption spectrum. And we might want to look at the two transitions separately by saying opt.output equals separate, and include that as a third input to Pepper. I misspelled that, separate, voila. And now you can see that there are two transitions, two powder transitions, and one is much weaker than the other due to the thermal polarization. Next thing to briefly mention are multiple components. So you can have one pepper call and include multiple components at the same time. So let's start out clearing everything and define a first spin system with like G values 1.95, 1.98, and 2.05, and some broadening, just convolutional broadening in millitesla. And let's then take a second system that has slightly different G values. You know, that's something you often can encounter if you're looking at catalytically active species, like intermediates of catalysts or in enzymes. Let's say 2.17 or so. And let's make this line a little broader. So you can simulate the spectra of these two at the same time, if they're in the same sample, by a single pepper call. Let's define the microwave frequency and the field range, 300 to 400 millitesla, gigahertz for the microwave frequency, and it's called pepper. And now you have to use curly braces, which indicates a cell array in MATLAB. In MATLAB, you have different types of arrays for those who are new to MATLAB. First of all, there's numeric arrays, where each element in the array is just a number, right? Then you can have cell arrays, which are also arrays, but instead of just a number, you could have anything in that array. You could have in the first entry, you could have a number. In the second entry, you could have a string. In the third entry, you could have an entire matrix, and so on. So a cell array is kind of allows you to build buckets and lists and collections of different things. And here, as for a cell array, you have to use curly braces instead of square brackets. So since we're going to put two spin systems together, and each spin system is a structure with fields, we have to use curly braces. So sys1, comma, sys2. That makes a little cell array with two elements, where each element is one of the spin systems. And comma, and then the experiments. And that's it. If you now press Control Enter, sys2, I have to define the numbers here. We have sys1 and sys2. Voila, and now you can see we have an overlap of two spectra. We see this one here with a peak here, here, and here at high field. And then we have the other one, which has sharper features. This is now a 50-50 mixture, but you can also modify the relative weights, so the relative concentrations of the two species, by adding a field called weight. And let's say the first one is a 30% abundance, and the second one has a 70% abundance. Now if you look at the spectrum again, I write this at 50-50. If I run it again, it's now 30-70. I could reduce that to like 10-90, right? And then you can slowly see that one component is vanishing relative to the other. So this allows you to simulate mixtures in one go with one call. And an important thing to reiterate here is that pepper is spin calibrated. So if you say 70% of one spectrum and 30 from the other, it truly means that 70 out of 100 spins are from the first species and 30 of the 100 are from the other. So you can actually use this to quantitate spectra relative to each other. So for example, if you have a solution of a radical with unknown concentration, but you add another radical with a known concentration, and you get overlapping spectra, if you're able to simulate them, you can read off from the EasySpin weights, you can actually read off what the relative concentrations are. So this is concerning multiple components. Next, important topic, crystals. For some of you, this is the bread and butter, especially if you're looking at defects in solids or small molecule crystals. So EasySpin is fully built out to handle single crystal simulations, and we'll do a very brief overview here. Let's start with a very simple spin system, some spin 1/2 electron with a G tensor of 2, 2.1, and 2.2, and again just some convolutional broadening of 0.5 millitesla. Now we're going to add a microwave frequency of 9.5 gigahertz and a range as usual, maybe 300 and 350 millitesla. And let's simulate the powder spectrum. First, we're going to ask Pepper to return us the data instead of just plotting them. Right, and probably should clear the figure at the beginning so we don't have that previous plot. I'm going to run this now. Voila, and everything's clean. Okay, next, we're going to actually specify a crystal orientation, right? If you do it on a crystal, you have to orient it in a spectrometer, and this orientation needs to be communicated to EasySpin. It's done by a exp.crystal orientation equals, and then you just have to give a triplet of Euler angles. Say 30, 20, 40 degrees. We have to convert it to radians as usual. Okay, and now let's simulate the spectrum again, this time the single crystal spectrum, because we added exp.crystal orientation. Let's see how that looks like. We're gonna probably just make two subplots, subplot 211, where we're gonna plot the powder spectrum is spec 0, and subplot 212, where we're going to plot the crystal spectrum. Okay, I'm going to run this now and let's see what happens. Okay, now on top you can see the powder spectrum. It extends most of the field range. And on the bottom you can see a single crystal spectrum with just a single absorption line. And this is determined, this is a function of the orientation in the of the crystal in the frame. So if I change one of these angles, then the orientation, the resonance of the crystal changes, the resonance position. Now, the molecule within the crystal is still assumed to be aligned. So the crystal itself is associated with an XYZ frame, and the spin carrying molecule as well. And what you can do, you can specify the relative orientation between the molecular frame, so where the spin bearing molecule, and the crystal frame, which is related to the ABC axis of the crystal. You can do this with exp.molframe. And let's say we're going to give this in radians directly now. Again, you give 3 Euler angles. And if you run this, of course, you will get a different resonance position, because now I've tilted the molecule within the crystal relative to the crystal faces and crystal morphology. So crystals, of course, have spatial symmetry, not just rotational symmetry. And as you know, in EPR, it doesn't matter, you know, whether the molecule is on the left in your sample tube or on the right. EPR is insensitive to translations. But in crystals, these needs to be taken into account because they lead to different space groups, symmetries of the crystals. So there's 227 different space groups for crystals, and they result in multiplication of those crystal absorption peaks, because the same molecule could occur in different orientations within the crystal. And in order to specify a space group for a crystal, all you need to do is to add exp.crystal symmetry, and then just give the number of the space group. 1 is the easiest, and that's the one that it assumes by default, and then there's just one line. But let's just pick another one. That's a space group number 50, and then you get 2 lines because it has a higher symmetry. Or space group 100, you get 4 lines. Or if we go to the highest symmetry space group 227, right, you end up with probably about 12 or 16 lines, probably 12 lines. That can make this a little narrower, then we get better resolution. There you go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get 12 lines, and these 12 lines are due to paramagnetic molecules within the crystal that have 12 different discrete orientations. And these orientations and how they relate to each other are specified with this crystal symmetry space group. So now let's say you have this crystal, and let's go back to a simpler space group again, so we have not too many lines. That's only 2, or let's say it gets 4 lines here. Now let's just say you have your crystal in there and you want to rotate the crystal. Right? And all you need to do a little rotation is you have to define which lab frame axis you're doing the rotation around. And if you recall, the lab frame is defined such that the z-axis is the magnetic field, so that's horizontal typically, and the microwave oscillating magnetic field is vertical in a typical resonator, and that's also the axis of the sample tube. Right, so the x-axis of the lab is going to be the sample tube, and we're going to rotate around that sample tube axis. Okay, so let's define, I'm gonna do this here. XL, lab frame axis of 1, 0, 0. Well, that's the direction of X in the XYZ frame of the lab. And then let's rotate it by 10 degrees. Again, it needs to be in radians, because that's the conventional angle unit in EasySpin. And now to tell Pepper or EasySpin to rotate the crystal by 10 degrees around the x-axis, you just have to say x dot sample rotation equals, and then a cell array with the rotation angle, rho, and the rotation axis, XL. That's all you need to do, and you can just basically step the angle through and see how the spectrum changes. This is new in EasySpin 6, so if you're using EasySpin 5.2, you can't do this, and it's much more complicated in the old EasySpin version. So if you're using crystal, if you're doing crystal simulations, I encourage you to update to EasySpin 6. All right, so what happens now? Let's start, see where those 4 peaks are. 10 degree rotation moves those peaks somewhere else. And if you want to explore how this changes, there's a little neat feature of MATLAB. If you have a number and you want to change it and rerun this section, you just right click on it, and then the first entry in the local menu will say increment value and run section. If you click on that, it opens a little menu where you could say, okay, I want to add or subtract degrees or number values from this, and that say 5 degrees, and if I click on the plus, it will increment that number by 5 and run the whole section. So while I do this now, look over at the spectrum and see what happens. Plus 5, 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 and so on. As you can see, as we rotate the sample, these resonance lines move around, and we have 4 different orientations within the crystal, and each of these orientations behave differently. So this is how you do crystal simulations. Just the basics. Next thing, it's 11:07, 11:30, 11:20. Okay. Next thing, parallel mode EPR. So sometimes, especially for integer spin system, you will not be able to observe a perpendicular mode X-band EPR spectrum, in which case it's good to simulate parallel mode. And EasySpin supports that out of the box. So let's take like a spin system. Let's take S equals 2, which is, which is a spin quantum number where you typically don't see any X-band data. So this could be typically for example, on Highspin iron 2. Let's add a really large zero field splitting, let's say 300,000 megahertz, which is 300 gigahertz. And let's keep it slightly rhombic, so with an E value of 0.1, E over D. So again, don't forget to specify tensor values, principal values in megahertz, even if they're very large. sys.lwpp, some broadening, just for simplicity. Then let's go to a standard microwave frequency, X-band. Now let's sweep the full magnet. Let's say we have a smaller magnet and it goes up to like 600 millitesla. And let's go simulate the spectrum. And by default, this is actually using perpendicular mode EPR because that's the normal vanilla EPR we're all doing. And you can be explicit about that by saying x.mode equals perpendicular. And then now let's simulate the same spectrum using parallel mode. All you need to do is change x.mode to parallel, and it will internally switch the way it calculates the intensities, then the transition matrix elements, and that then gives you the parallel mode EPR. We can plot the 2 spectra and see how they look. Control Enter again runs this whole thing. It's taking a little time, and voila, I should have probably deleted this figure here. So you can always delete a plot by clicking on the figure, then going to the figure ribbon menu and clicking on that little cursor. And then you edit plot mode which allows you to select individual things within the plot and then press delete just to remove them. Or I can remove the entire axis. I can click here and I can enlarge this. Voila. Okay, now you can see we've got in the perpendicular mode spectrum in blue and the parallel mode spectrum in red. The parallel mode spectrum is much more intense. What you see are some kind of oscillatory features. This is again simulation noise. We don't have enough knots. So what we need to do is we need to increase the number of knots. So up.n knots equals, let's try 31. And include options in the two calls and run that again. And if you look here at the bottom left, in the very tiny thing at the bottom, it will say busy. That tells you that it's running. Also, if you're on the editor panel, it will show a pause button here instead of a run button, and that will tell you it's running. Okay, we still have the number of knots is not sufficient. Let me double those to 61 and see if you get a difference. It's running. As you can see, if you have a higher spin system and you have a lot of orientation, the simulation can actually take quite some time. We'll wait until it concludes here. Voila. Now it is concluded, and you can see that we still have some oscillations, but they're much smaller. The fact that you still see oscillations means you just have to increase the number of knots further. You know, if you're only interested in this low feature, you might disregard them for now and just focus on this. But then if you want to simulate a publishable spectrum that's smooth and simulated, increase the number of knots. You can also see that the parallel mode or the perpendicular mode spectrum in blue is affected much more. It's not as smooth as the parallel mode. So if you just look at the parallel mode, again going to the figure window and deleting the perpendicular mode here, grab this. You can see that's actually fairly smooth. If you zoom in, you will see a little bit of simulation noise of incomplete averaging. But that's probably totally bearable, even if you go into least squares fitting analysis, which we're going to talk about a lot more tomorrow. So the last thing I'd like to mention in this second session on solid state EPR are spin polarized triplets. Often there is a system when you photo excite them into an excited singlet state, they transition over into an excited triplet state via intersystem crossing. And these are, of course, EPR active species, with a difference from the standard triplets that they don't have thermal polarization, but they have non-thermal populations on their energy levels. And this can be done in EasySpin fairly straightforwardly. So let's take this a little further up here. Let's clear the figure and define a triplet. So that's a spin once system. Let's put a G value of 2 and give it a D value of like 342 megahertz with 21 for the E value. These are the actual numbers for the excited triplet state of C60 of Buckminster Fullerene. Now, in order to specify these non-equilibrium populations for a spin polarized triplet that came into being through a singlet triplet intersystem crossing, use sys.pop, where pop stands for populations. And these three population numbers, we can put 1, 0, and 0 in there. These refer to the energy eigenstates at zero field, because that's typically how these states are the ones that are being populated by the intersystem crossing. And these numbers don't add up to 1. And they will depend, which numbers they are, depend obviously on which system you're looking at. So yeah, add some line width, define the experiment, some numbers here, 310, 350, and x.harmonic equals 0, because we're going to look at the absorption spectrum first. So if you are familiar with this and you're using EasySpin 5.2, you will notice that this is actually new. This is new in EasySpin 6. It's a much cleaner interface than in the old version, where this was mangled into the temperature field. Okay, let's see how this looks. I'm pressing Control Enter, and voila! Now you see this is the absorption. There's a zero harmonic spectrum. So any positive intensity is absorption, and any negative intensity is emission, right? And you can change the populations here, and you'll probably see some changes in this spectrum. Voila! And you can even look at the transitions separately. So say opt.output equals separate. Put that opt in as a third parameter, and run again. And now you can see these are two transitions. It's a triplet, right? So there's 3 levels, and you can have 2 transitions between adjacent levels. And depending on orientation, each of those transitions is either absorptive here in the high field edge, or it can become emissive in on the low field region. So this is valid for so-called intersystem crossing triplets that come from a singlet to triplet transition. If you have triplets that are generated from radical pairs, then the mechanism is slightly different, and you can't use cis-pop directly. But you can find more about this in the documentation. So these are a few additional topics for solid-state EPR. In general, please always go back to the documentation. It's fairly extensive. There's a user guide on doing solid-state EPR simulations. There is a separate one for single crystal simulations, and yet one more on spin polarized systems. And you might also want to look at the reference page for Pepper, which is kind of, I would say, the core function of EasySpin. It's been around the longest. I think with this, I'm at the end of my plan for this session. I think we're doing good time-wise. So the next session will be a Q&A session. And I think Stefan Pribitzer has already compiled a few questions he found on Slido, and I'll also have a look in the next couple minutes, and I'll see you back then at the Q&A session, where I also will show you how to access the happy hour space at GatherTown. Until then, enjoy your break or look at the documentation or the exercises. Bye.